Okay, just heard was probably
Right, it was.
joining the call. Okay, very good. So we're recording. Pause it.
I mean, otherwise you're just going to have this.
Okay, great. So just another second to get started. Okay, it's 3 o'clock, so I'm going to run through logistics, and then I'm going to turn it over to you, okay?
Sounds good.
So thank you, everybody, for joining. This is the second webinar of 2 on black carbon, which is being hosted by the Interagency Arctic Research Policy Committee collaboration team on atmosphere. And we're pleased to welcome you to this webinar, which will be moderated by Tennille Utah at NOAA Esrol. And our collaboration team, is chaired by Wanda Farrell, Ashley Williamson from the Department of Energy. So for those of you on the audio, I presume that you all are on the webinar. If for some reason you are not on the webinar because your workstation doesn't support WebEx, all of the slides are available on the website, which is listed on the agenda. And you can get there through the ARCIS website, which is www.arcis.org, and click on IARPIC webinar and go webinar 2, and you can get to all of the presentations, which are on PDF there. I'll just run through. My name is Sarah Bowden, and I am the Secretary for IARPIC, and I just want to run through a couple logistics for this webinar. Again, thank you for everyone for joining. We have no voice over IP, so the only audio that's available is by phone. So ask everybody to please mute your phones. Even presenters who are not presenting at that moment, please mute your phones. And if for any reason you need to leave the line, that's fine, but please do not put us on hold. If you need to leave, that's fine. No hold. We will be taking questions after each speaker, just a couple directly for that speaker. You can ask the question by sending a chat in the chat box to Tennille Utah, the convener, and she will then read back your question to the group, and the presenter can answer it. Or you can unmute your phone and ask the question back to mute for the answer. Tennille? Sorry. Tennille?
Hi, Sarah. That's not us.
Not you.
Somebody's
okay.
clacketing in the background.
So everybody, please go mute. Wow. Okay. It's really important that everybody is on mute. Let me just send a message to all to please mute. I'm going to turn the webinar over to Tennille. We do have 15 minutes at the end for more questions in the chat box, or you can send by unmuting your phone and ask Tennille to raise a question. So do us the favor of everybody muting. Somebody is not on mute, so please check your phone and make sure you're on. Okay, Tennille, thank you.
welcome everybody. This is Steve. I'm from the National Oceanic Administration, and I am part of this atmospheric implementation of Arctic that Sarah just introduced. This is the second in a series of carbon seminars. First was on March 28th, and we had a number of speakers from DOE, EPA, USDA, and the State Department that were talking about U.S. black carbon mitigation activities and initiatives that are currently in progress. We are following the webinar with a second one now that is going to be more focused on some of the foundational science research that's going on about black carbon in the Arctic. I'd like to give a very quick little that we have for some of the questions and issues that we came out of the first seminar. One thing that we noticed was that USDA and DOE have different techniques to evaluate the potential of sources in the country that I will only refer to as the R country to attack the Arctic, and how the estimates of source and receptor relationships compare, and then how do they compare from what we know from other studies. Another question, free question, and I'll say that Terry Keating came up with these very nice summaries. Emission inventories be integrated into, and how can regulatory emission inventories be integrated with and supported by foundational science efforts? I think for the purposes of this seminar, the important questions that we'd like to be able to address on an interagency basis, informed from the talks during this seminar, of past black carbon observations in the Arctic and their observational data to support model evaluation and source apportionment, and also observational capabilities in the Arctic to improve source apportionment. With that, I'm going to introduce our first speaker. We have three speakers today: Trish Quinn, Rex Kahn, and Mark Jacobson. I will introduce each of those speakers and tell you a little bit about them before they begin talking. Our first speaker is Trish Quinn, who is a research scientist with the National Oceanic and Atmospheric Administration, and she is currently the co-chair with Andreas Stoll of the Arctic Monitoring and Assessment Program Group on Short-Lived Climate Forcers. AMAP is one of the 6 working groups of the Arctic Council, and she was the lead author on the 2011 AMAP technical report on black carbon on Arctic. And the topic of her talk is going to be the impact of black carbon on Arctic climate change, not surprisingly. With that, Trish, I'm going to turn over the controls to you.
Thanks, Tanil. Focus on the work that AMAP has been doing since 2009, and it's still ongoing. So I'll show you some results of model simulations that we've done. Just want to start with an introduction. I'm sure we're all aware that observed sea ice loss in the Arctic has occurred at a faster rate than predicted by models. Proceeding into this includes anthropogenic forcing, which is warm due to greenhouse gases, variability in climate patterns, and albedo feedback. But more recently, over the past decade, people have started consuming short-lived pollutants is also playing a role of warming the Arctic and leading to sea ice loss. So, just by definition, short pollutants are typically considered to be black carbon and tropospheric ozone, which have lifetimes of days or weeks.
Excuse me for just a minute. I'm going to implore our audience to please identify the person who has some kind of background noise going on right now. We hear sneezing and rustling and rumbling, and somebody could please be on mute now, except for Trish.
Okay, thanks, Tanil. And methane, which has a lifetime of about a decade, but still much shorter than that of carbon dioxide. So what I'm going to talk about is just when Arctic forcing, so looking particularly at black carbon. And so when we're talking about within Arctic forcing by black carbon, we have to somehow get that black carbon transported to the Arctic, since sources in the Arctic are limited. So this is a cartoon, the Arctic front, and it shows you an orange line, which is the front during summertime. It's much more confined to this small high latitude region, and the winter time front is shown in blue. And this is basically a temperature gradient that forms a barrier to the transport of pollutants into the Arctic. And you can see that the wintertime front extends as far south as 40 degrees north over northern Europe and Asia. So northern Eurasia is the major source region to the Arctic at low altitudes. And this happens because it's cold air in the winter, snow-covered surfaces, reduces the temperature gradient, and there's a lot of pollution sources in this region. So it's easy for them to transport in at low altitudes during the winter and spring. Other source regions, which are further south and warmer, can also have emissions come in the Arctic at higher altitudes. Also, you can have convective fire plumes that can reach quite high altitudes and go into the Arctic higher up. This is just a picture of aerosol scattering and aerosol absorption and black carbon at Barrow, Alaska, and Alert in Canada. And it just shows you the seasonal cycle where every winter and spring you get a spike of pollutants coming in at low altitudes in the Arctic. This is a forcing diagram that came out of our AMAP 2011 report, and it just shows the complexity of forcing by black carbon and aerosols as things are changing in the Arctic as the sun comes up and melting starts. But in winter, when it's still dark, adding pollutants to these thin clouds makes them act more like a blanket, and you get more long-wave emission back to the surface, which serves to warm the surface. In the spring and early summer, you can get deposition of these black carbon-containing particles, which leads to a darkening of the surface. And in summertime, with a lot of solar energy, you have aerosol with clouds and increasing the albedo of the cloud and leading to a cooling of the surface. And similarly, black carbon-containing aerosol absorbing energy and that layer of the atmosphere, but eventually that heat can get mixed down and warm the surface as well. Tennille introduced what AMAP is. This is just a schematic of the Arctic Council, and it's made up of all of the countries that border the Arctic. And underneath the Arctic Council, there are 6 working groups. AMAP is the Arctic Monitoring and Assessment Program. And in 2009, the Arctic Council decided that AMAP should form an expert group on short-lived climate forces. And the goal of that expert group was to provide scientific and technical advice regarding formulation of mitigation strategies, assessment of Arctic climate benefits of mitigation strategies, coming up with effective measures to reduce emissions, and then recommend action items for further research. So this is a report that came out of that. It's on the AMAP website, and it has some background information on black carbon, including emission regions and also source sectors, properties of black carbon, transport pathways to the Arctic, trends in Arctic BC in both snow and aerosol, and also model simulated radiative forcing for black carbon within the Arctic. That we wanted to address by the AMAP model simulations were which geographical regions have the largest impact on the Arctic in terms of emissions of black carbon and associated within Arctic radiative forcing, which combustion sources have the largest impact on the Arctic. So our approach, we have emission inventories. We have 2 climate models which then supported these emissions to the Arctic, perturbed the composition of the Arctic, and then we calculated the radiative forcing associated with that distribution of black carbon-containing aerosol. We had a short timeline for this report, so we didn't have time to actually calculate the climate response. We stopped at the radiative forcing. This is something we're doing now on our activities currently. Simulations included black carbon and co-emitted particulate organic carbon, calculated black carbon, snow albedo forcing, and the atmospheric direct forcing. And broke up the different geographical regions as follows. We've looked first at the Arctic Council nations. So this includes the U.S., Canada, Russia, and then we lumped the Nordic countries together. But we wanted to know how the rest of the world was impacting the black carbon in the Arctic. So we divvied it up by latitudinal bands. We had one large band going from 90 south to 40 north, and then 40 to 50 north, to 60 north, and then the Arctic itself, 60 to 90 north. Our different emissions included domestic combustion, transport, which is primarily diesel engine combustion, production and industrial processes, agricultural fires, grass and forest fires, and then we also looked at current and projected shipping emissions. This, I'm going to show you a bunch of plots that have this same format. On the left, council nations, and then on the right is the rest of the world. And this is emissions of black carbon, and the different colors refer to the different source sectors. So you need to know that the two different plots for the Arctic nation, Arctic nations versus the rest of the world are different by order of magnitude. There's about an order of magnitude more black carbon being emitted in the rest of the world than in Arctic Council nations. But again, we have to look at what portion of this black carbon is actually transported to the Arctic. I'd also point out that for the Council nations, for Canada and Russia, it mainly comes from forest fires. US and the Nordic countries are mainly diesel emissions, and the rest of the world is a pretty mixed bag. So again, you have to consider both emissions and transport to get the contribution of each source and region to the burden of black carbon in the Arctic atmosphere. This is showing the kilograms of black carbon actually transported to the Arctic. And first you'll know that the Arctic Council nations and the rest of the world are on the same scale, so it's really only a very small fraction of the rest of world black carbon emissions that make it up into the Arctic. In fact, if you sum up the burden of black carbon in the Arctic due to the Arctic Council nations, it's pretty comparable with what gets up there from the rest of the world. And we calculated the forcing. So this plot is the same thing, Arctic Council nations on the left, rest of the world on the right, and the solid bars are for the black carbon snow albedo forcing. The hatched bars are for the atmospheric direct forcing. Again, it's pretty comparable in terms of forcing between summing up the Arctic Council nations and looking at the rest of the world. Let's move on to the next. So here looking at the emissions from different latitude bands. So this is going on the leftmost from the southern hemisphere up to 40 north, 40 to 50, then 50 to 60 in the Arctic itself. And there's an increase in the forcing as you get closer to the Arctic. And so that since this is the black carbon albedo forcing, it's just saying that sources closest to the Arctic are most likely to be deposited to the surface. And the forcing within the Arctic itself is small just because there's so few emissions. This is the same type of plot for the atmospheric direct rate forcing. But you see this fairly large estimated forcing from 90 south to north emissions that make it up into the Arctic. And most likely forest fire emissions coming from lower latitudes and entering the Arctic at a higher altitude. This is showing the impacts of current and projected shipping emissions of black carbon. So left is just the absolute 40 watts per meter squared, and you can see that there's 2005 levels of emissions and going up to year 2050, and it's quite large for the global in terms of compared to the within Arctic forcing, just because there's so many more emissions globally than in the Arctic. And then a small increase in the forcing within the Arctic due to more ship traffic going out to the year 2050. On the right is the forcing per unit emission, same plot, but now it just shows you how impact emissions in the Arctic could have on the black carbon snow albedo forcing, and indicates the potential importance of limiting emissions in and close to the Arctic. So, at that exercise in 2011, these were the things that we felt that we could say for sure, that source regions and source types that dominate the burden of black carbon in the Arctic are fairly understood. Forest and grassland fire emissions dominate the contribution from Canada and Russia. Agricultural fires can also make a significant contribution if they turn into forest grass fires. These combustion emissions dominate the contribution of U.S. and Nordic countries to the burden of black carbon in the Arctic. Domestic, mainly wood stove burn within Nordic countries and Russia, make a substantial contribution to the burden of black carbon in the Arctic. And as the regulatory emissions increase on transport emissions, the relative importance of these domestic sources is likely to increase. Emissions in close proximity to or within the Arctic are more likely to be deposited to snow and ice surfaces and cause surface warming than emissions from further south. And one thing I haven't talked about and that we did not really consider in the 2011 assessment was extrapolar forcing likely results in poleward transfer of heat energy, indicating the need to manage global emissions of black carbon. Our next steps, this last report include black carbon and co-emitted organic carbon. Currently, we have model simulations running include sulfur dioxide, nitrogen oxides, methane VOCs, and tropospheric ozone. Also included flaring, gas flaring, which we didn't have in the last assessment. So a recent paper by Andrea Stoll showing on the left the simulated annual mean surface concentrations of black carbon due to gas flaring, primarily in Siberia, and then comparing that to all other sources of black carbon around the Arctic. And the model simulations done by Stoll et al. Indicated that gas flaring is estimated to contribute less than 3% globally to black carbon emissions, but at the surface in the Arctic, it can contribute up to 52% of all black carbon in the springtime. What we're doing differently this time is looking at monthly biomass burning, agricultural waste burning, and domestic combustion. Again, the same study by Andrea Stoll. They should not taking into account seasonally varying emissions may be causing model biases in the simulated black carbon concentrations in the Arctic. This figure in the top plot is for the month of January and showing you the black carbon concentrations in the atmosphere as a function of height. And you can see it really dominated by domestic combustion or using a wood stove for heat. And the bottom plot, it shows the emissions for, or the black carbon concentrations for July being more dominated by biomass burning. As I said before, the one thing we're doing this time also is going further to look at the climate response emission reduction scenarios with several fully coupled ocean, atmosphere, Earth system models. And I believe, this is a timeline. We're sending our first out for review by national experts now. This is mainly just to see if there's any data or information that we're missing that we should be including. Peer review in August, and then it's expected to be published by AMAP in early 2015. So that's all I had. Thank you.
Thanks very much, Trish. That was many questions showing up on our chat bar, and I think probably that indicates that after everybody has a chance to absorb all three talks, we'll probably do most of our questions at the end. But I will give an opportunity for a moment now if anybody would like to unmute and ask a question directly. John Grin, it sounds like you'd like to pipe up here.
My question is really going to be related to our next talk. and that is if you included aircraft emissions.
Well, yeah, we had aircraft emissions in the transport sector, but didn't separate out on its own.
Actually, the contributions will be Mark Jacobson will be the talk after Ralph Kahns. That'll be next now.
And we also have a question from Randy Jant. Were emissions from Alaska forest fires included in the U.S. contribution? What years were used for the mean?
The mean year was 2005, so yes, they were included. So yeah, it's totally, I mean, the answer you get out of the model definitely depends on what year emissions you put in, especially for forest fires.
Actually, Sandy, I had written down a question. Sandy and I are in the same office, and she prompted me. Could you talk, it sounds like so much of the burn of black carbon in the Arctic is based on these emissions and modeling trajectories. And could you comment a little bit, Trish, about what kind of emissions you think that we could make with in situ observations at observatories at Arctic regions?
Definitely. I think that these attribution of black carbon sources to the burn in the Arctic are based on inventories and models getting them, getting those sources transported to the Arctic. I think it would be really valuable to have an in situ measurement program where you were measuring black carbon or a proxy of it, like light absorption, and looking at also trace species that are able to tell you something about the sources. And you can do this in the air and in the snow to see what black carbon is actually getting deposited to the snow, so or from aircraft.
Great, Trish. And we have another question. I live in Alaska. Do you think the BC emissions in the areas you mentioned may also impact glacial systems in coastal Alaska, southeast Alaska? I accelerate glacial recession.
Yeah, certainly if there is an impact of black carbon on glacial recession, it could, and those fire emissions or whatever's being emitted in the region get deposited, then it's possible. We have done some measurements but compared them to measurements further south in Poker Flats, and know that the stuff that's coming across the pole south down through Alaska doesn't make it across the mountain ranges, so there's some blocking to getting some of the Arctic pollution transported down to southern Alaska.
Okay, everybody, that's it for questions, it looks like. I think we're going to move on to our next speaker now, who is going to be Ralph Kahns. Ralph is a senior research scientist at NASA Goddard Space Flight Center. And I wrote down in my little bio here that his work focuses on using MISR's observations combined with other data and numerical models to learn about wildfire smoke, desert dust, bulk and air pollution particles, and to apply the results to regional and global climate change questions. We're lucky that Ralph coincidentally happened to be in Boulder today, and we actually have him here in person so we can watch him do his presentations. And he did mention that he does much more than work with just MISR observations. The topic of his talk today is going to be satellite constraints on Arctic region airborne particles.
Okay, thanks, Neil. Well, satellites, how do we know what we know? That was kind of the question that I started with. Satellites are fairly blunt instruments for studying a lot of detail, and in particular in the Arctic region, as you'll see in a minute. But do provide us with frequent, large-scale coverage, and so that's the advantage when you're talking about large-scale transports of material. Satellites would be probably the best tool to do something with that. So how do I advance the slides?
I think maybe the space bar is, oh, I'm
Oh, this is a busy slide. It's the only one. I wanted to give my conclusions kind of at the beginning. So they are. Aerosol remote sensing is an especially challenging thing in the polar regions due to a combination of factors. That includes a very bright surface, low sun angle, persistent clouds, including cirrus, which matters if you're trying to retrieve aerosols, and generally low aerosol optical depth. Some success has been obtained, and I'll show some examples of this, of retrieving optical depth over incomplete snow-covered surfaces, but that's very difficult to do if the surface is completely snow-covered. Despite very limited coverage from space-based LiDAR, active sensors, Calypso LiDAR is by far the most sensitive and in some ways the best available space-based total column, height resolved aerosol observatory. And especially at night, and this is another interesting thing you'll see, the signal to noise is much better at night when there's no reflected sunlight, and so you actually get a better signal at that time. Another unique but relatively poorly sampled source are limb sounders, and the SAGE instruments are a good example of that. They also provide height-resolved aerosol extinction profiles, but they don't go all the way down to the surface because they're looking over the long path of the atmosphere toward the limb, toward the sun. So both of the active sensors and the SAGE.
I'm just seeing a note that people can't hear you very well, so maybe we'll try to move the phone a little closer.
All right. Can you hear me now? Okay. I guess that's a yes. So from these instruments with poor sampling tend to be averaged a great deal. Imagers like Modus, Miser, TOMS, OMI, and others, they provide broad spatial coverage, but they have all the issues that I mentioned in that first bullet there. But essential for making event-resolved studies of any sort. And so the result is that we, in the subarctic, we use the passive sensors to characterize the sources, and then transport models are very effective in getting climbed up the bottom. Yes, I did. Thank you. I'll stop by later, by the way. So, now molecules also serve as interesting tracers that can be used. So CO and SO2 are two very good examples of that. CO being a tracer for smoke, for wildfire smoke typically, and SO2 being a precursor to sulfate aerosols in the stratosphere. And final point is that given the limitations of each of these approaches, a combination of active and passive satellite measurements, suborbital observations for validation and additional detail, and transport modeling trained by these observations is required to complete the picture of Arctic aerosols. So now the rest of the talk is examples, and it's not advanced.
You have to click the little arrow right here.
I have to click the little arrow right up there. All right, here we go. So these are examples of coincident data between the Miser instruments and sun photometers on the surface in various relatively high latitude sites. And you can see the sites are listed there. Difference plots of the aerosol optical depth, the amount of aerosol in the column between retrieved values from space and aeronet values that are determined from a sun photometer on the surface, which is a very good way of getting aerosol optical depth. So the first thing to point out is that if you look at the little black boxes under each plot, you'll see a number of coincidences between Miser and the surface sun photometer at which both provided retrievals over a period of years. Bear in mind that Miser observes the entire Earth about once a week, and at high latitudes it's every 2 to 3 days. So for example, let's take the Tomsk one in Russia. Over 5 years there was a total of 29 coincidences. For the case at Gotland, over 3 years there were 21 coincidences. So this combination of cloudiness and other factors that affect the ability for us to do retrievals have this very low number of coincidences, so it's difficult to do the monitoring. The other thing I want to point out is circled in green under Barrow. Barrow is one of the few sites at the surface that actually takes data when there's much snow on the ground. And you can see there's an anomaly. The dots go above the dotted line because MISR is retrieving too high an optical depth relative to the ground elevation, and the reason for that is snow contamination from the bright surface. So this is an illustration of the issue that we have doing retrievals over snow and ice from satellite. So the issues, once again, the optical depths are generally low. Most of them are below 0.2, and you can look at the plots and see that almost all the points are on the left side. The sites, most of them snow-free during operation. If they're not snow-free, another issue for Aeronet, even though they're very good observations, is that the reflection from the surface actually can make a significant contribution into the sun photometer field of view. And so that's to be corrected for, and I don't know that anybody's actually done that. So making those observations even from the surface under snow-covered conditions does not work. About 8 sites, I'll illustrate those in a minute. And the persistent cloudiness and the low sun angle are all the issues. So moving on here. So these are some of the Internet sites that were operative at any time during 2013. And in some cases, there may only be just a few observations. This is the Western Hemisphere in the north. This is the Eastern Hemisphere. This is the story from the surface. Now, we'll start with the optical depth. This is Nimbus 7 tons data, and we got here from Omar Torres' 2002 paper our monthly, for 4 months of the year, examples of the sources. And what you see, for example, is that in winter there's no signal. So in January and February you get no signal. In the summer, July and August, you do get signal to high latitudes until the sun angle gets too steep. And you can see I put a couple of arrows near some smoke sources in July and August on the upper right of the figure. Most of the sources, as Trish was mentioning, are either from fires of one sort or another or from pollution. And this is that's month averaged, aggregated over a number of years, as indicated in the title. Okay, so in MODIS, so the TOMS data is doing a retrieval in the ultraviolet. MODIS do it in the visible and use some near infrared. And this is 1 day's worth of data from these two instruments. So I'll point out a couple of things here. High latitude observations are not nearly as well sampled as the lower ones. You can see that in the MODIS data as well as in the MISR data. MISR has a narrower swath, but it has multiple angles. And makes it possible to do retrievals over partly snow-covered surfaces. And I have those outlined in black in both. You can see MODIS, which is just a single view, large swath here, whereas it has 9 cameras looking at 9 different angles. And so we're able to get optical depths over some of the regions where MODIS cannot do it. And then you see some black arrows. That's over water, and there's sun glint. And again, if you have a single view, you're in sun glint, you can't do an aerosol retrieval. But if you have multiple cameras at different angles, you're in a position to fill in some of the missing parts of MODIS. So this is the kind of coverage we have from the satellites. Okay, so now we go to the active sensors. This is Calypso mid-visible optical depth. This is 5-year zonal average. So along the horizontal axis here are different latitudes. I put a yellow arrow at the high latitudes. It's vertical information and latitudinal zonal averaged information giving the mid-visible optical depth. And you see one thing which Trish mentioned too, and you can see it now in the data, which is that on average the aerosol is concentrated very, very near the surface. And you can see that right below the arrow. The yellow arrow, the red part is the major concentration of aerosol. And due to the low sampling frequency, a great deal of averaging is required in order to create a picture. And then finally, on this slide, I wanted to just mention that the nighttime images are used only, exclusively, because the signal to noise is high at night. This is from Dave Winker's paper on the subject. I've got a couple of slides from that paper because he's done a nice job of aggregating the Calypso data in different ways. So now a collection of seasonal averages taken over 2008, and you see another thing, which is that at high latitudes, the optical depth here, which is what's plotted in the mid-visible, is very low. It's lower than 0.1 in the seasonal average. The other thing you see here is that unlike the visible and UV imagers, Calypso data has missing data in the summer rather than in the winter because you don't want to be looking during daytime. So I think that was as much as I wanted to say about that one. Another somewhat more detailed polar image from Winker's paper, and you can see that there is zonal variability in the optical depth, even based on this highly averaged, and this is now averaged from 2007 to 2011 during the winter season, optical depth from Calypso, and you see the high optical depth over the eastern hemisphere, particularly Russia, that was mentioned by Trish, and it turns out that the lowest is over Greenland because the Atlantic, the North Atlantic, turns out to be a source because of sea waves breaking that produce sea salt that contribute to observations. Okay, moving right along, one more slide here. This is now the extinction scale height, which is how we're going into a lot of detail of the vertical distribution, and it's a small scale height at the highest latitudes here, and it's smaller over ocean than over land in general, and the aerosol is basically quite concentrated near the surface. You see, if you look over Greenland in the lower left plot, you'll see that Greenland has about the highest scale height of anyone, and that would be, fall in the late summer when the surface is presumably a bit warmer and the lower atmosphere is a bit warmer. Here, these are profiles, which just give you that idea. I wanted to show a little more detail here about that. So in January, everything is scrunched down near the surface, and you have that Arctic haze. And so you can see it's not a great deal of height, but you can see that the profile for March is somewhat higher than the profile for January, and it's still near the surface. Okay, so what can be done with this Calypso data apart from looking at highly averaged cases on a seasonal or monthly basis at the average over a number of years? By using a combination of information. Okay, so the Calypso instrument has two wavelengths and a polarization sensitivity, so you can get a backscatter quantity, a vertical profile of backscatter. You can get the ratio of backscatter in two colors, which they call the color ratio, and you also get the depolarization. And things like dust tend to depolarize, whereas spherical aerosols typically do not. And so able to do some kind of classification. This is fairly crude qualitative classification, but this was on a TELUS paper. You can see here it was aggregated over winter, spring, summer, and autumn over a period of 5 years. And clean continental aerosol, based on this classification, represents the background. Now, the vertical axis on these histograms is the normalized frequency of observation. It's not the quantity, it's just the normalized frequency of observation. And you can see that basically you have this rather substantial background of what they call clean continental aerosol. You see that there's this clean maritime aerosol, which tends to peak in the summer here in terms of the frequency of observation. It's consistently over the year in Greenland, and actually from the North Atlantic itself, it also peaks in winter when there's a lot of breaking waves. And then finally, you see the polluted continental and the smoke that tend to peak in the summer. So this is a crude classification based on frequency of Calypso data. Now, black arrow here has migrated up for some reason that I don't know, but the Tropopause is this white line across the top of this slide. This is now from the SAGE instrument, which is look at the limb. It looks at the atmosphere occults the sun, and as the path through the atmosphere goes down, you get a signal that progressively diminishes, and it tends to die out completely at about 4 kilometers or higher. This is, again, highly average data. This is 15 years of regional average SAGE data. This is the mid-visible optical depth. But you see the time peak in optical depth at high altitudes, above 6 kilometers. It's just below the Tropopause there, and that would be probably a fair amount of contribution from grounded aerosols over really long distances. To mention something about that you can get transports higher altitudes within the troposphere from distant sources. The other thing you can get from the color ratio is the particle size, and the particles are quite small, 0.35 to 0.25 microns in diameter. Now, this is probably the best seasonal vertically resolved summary that I was able to find in the literature. This is, again, Calypso aggregated data over 6 years, and you've got the columns are different seasons, and the rows are the high altitude, mid altitude, and low altitude information from Calypso. And you see in the first row, which is the high altitude transport stuff, you're looking at springtime high altitude transported aerosol from probably Asian sources and maybe some dust. In mid here, you see in the spring, summer, now you're seeing some forest fire smoke coming in to the Arctic region. It's not necessarily reaching high Arctic, but then there's also some limitations in the sensitivity. And then finally near the surface, you're seeing those near sources from Siberia and Europe dominating the scene, especially in summer, but throughout the year pretty much. And then in winter, you see that transport of probably sea salt. So there's also some interannual variability that tends to increase with the positive North Atlantic oscillation phase. I'm not showing that here. Okay, a couple more examples. I'm nearly done. I wanted to know how tracers like carbon monoxide can be used in this way. This is one of Jen Fisher's papers using the Geocell model and Airs data. Airs is a sounder that's sensitive to the vertical structure of temperature, humidity, and you can get CO column abundance from the instrument, and she's mapped that out here on the left side, and on the right side is the Geocell model, which has height resolved distribution of CO into the Arctic, and you can see the transport in the Arctic that occurs primarily in mid and low latitudes on this simulation. Another example of this, here it's again using the Geocell model, but here what we're looking at is the perturbation to the source of aerosol during a summer 2003 major biomass burning event in Siberia. And so at the top you see the fractional optical depth attributed to it. This is in August, the left and right panels at the top of the optical depths. And then the lower plots give you the deposition. This is a model that was constrained with Moffett CO data, carbon monoxide, and then optical depths from both MODIS and the Polder, which is another broad swath imager. And so passive sensors, they're needed in order to provide the source characterization that then the model transports to the polar region. So let me talk just briefly, a couple of slides here, about what we can say in the subarctic about the aerosols and their sources. This is now MISER data. This is our stuff I've done. These are now an example of wildfires in Alaska You can see on the left the image of the smoke, the optical depth of the smoke that we retrieve with MISR, and the angstrom exponent, which is a proxy in some very crude sense for the size distribution of the particles. And you see that the particles in the smoky region, which is outlined in red, are somewhat larger. They have a smaller angstrom exponent, which, without going into details, indicates that the particles are larger. The other here gives you an indication of the vertical distribution, which we get from stereo imaging from MISR. This is now a Siberian wildfire. You see the distribution of smoke is at about 2.5 kilometers. And I have also from the ENS model the atmospheric stability structure, and the smoke tends to concentrate in the low mid part of that stable region. Where am I going here? Next one. So we've done this smoke plume height characterization for all North America, and Maria Valmartin was a postdoc working with me, and we characterized 3,100 plumes over North America over a period of 5 or 6 years. And you see that many varies with season, with year interannually, and it varies with the surface type, what's burning. But there's a significant amount, somewhere between 8 and maybe 20% of the time, smoke is injected above the boundary layer, which means it gets to travel farther. I think this is my final slide. This was one of those grand canonical summations where the ECHEM5 model was used together with satellite and suborbital data, Calypso data, to constrain the model. And in this particular case, there was field data from ArcTAS that was used to help constrain the model. And what they found, one of the major conclusions there, was that they had to adjust their aerosol wet scavenging in order to reduce it, in order to be able to come up with convincing vertical distributions, which had an impact on their ability to model the various source regions as a function of season, which is illustrated in the lower panel there. So the satellite data by itself is a very blunt instrument, as I mentioned before. And I should say one other thing, and as we talk about black carbon, by satellite point of view, it's really just absorbed aerosol. It can be black carbon, it can be brown carbon, it can be pollution or wildfire smoke. We have some sensitivity to the differences of those in a crude sense, but carbon per se, for some chemists, has a very precise meaning of highly reduced carbon. On satellites, we don't have nearly the sensitivity to do that. On the other hand, we do provide this frequent global picture, which allows us to characterize the source regions and do some constraining on the models, and I'll stop there.
We've got about 3 minutes for questions. I'm looking at the chat and not anything coming up, so if anybody would like to unmute and ask a question directly, now is your time.
Martin Jeffries.
Martin, want to go
Hello.
ahead and ask Ralph a question?
No, my question's for Trish. When there's occasion, opportunity. Sorry.
We can do that at the end here, I think.
Thank you.
And I do have a question here I see in the chat. It is from Joshua Schwartz, and he said, is satellite typing valid after aging transport to the Arctic?
Oh, typing is done on the ambient aerosol, whatever it is, and the sensitivity that we have, well, it depends on the instrument. The Calypso sensitivity, which I discussed earlier, which I've shown a number of examples for, really is based on the color ratio, depolarization, backscatter. It's just the magnitude of the backscatter. It's just those 3 quantities they use. And so when the optical depth is low, it's very difficult to get that kind of information out. But times we're able to do it, and you saw some examples of that. ISER can do aerosol typing as well, but optical depths in the Arctic below 0.2 are too low, especially given the sun angle and the bright surface. So Calypso is the best game in town, and it can be good, but it's always. And that's another thing about retrievals of type. That is that retrievals to aerosol type varies enormously with conditions, more so than the retrieval of optical depth in most instruments.
Very much, Ralph. I think we're going to move on to our next speaker now. This will be Mark Jacobson, and my little intro for him is that Mark Jacobson is a professor of civil and environmental engineering at Stanford University and also director of the Atmospheric Energy Program. His focus not only on understanding severe atmospheric problems such as air pollution and global warming, but also to develop and assess large-scale clean renewable energy solutions. In 2013, he received the AU Ascent Award for, quote, his role in the development of models to identify the role of black carbon in climate change. Mark's talk today is going to be with the topic of contributions of cross-polar flights to Arctic black carbon. And Mark, are you there?
Yeah, Eric.
We see your presentation's up, and you should have the controls now.
I think I don't see the presentation on the screen.
So you see the tab where it says Jacobson right after Kahn?
Don't.
Top of WebEx.
Here, I'll take control back and just switch it to your presentation.
Yeah, be good. I don't see that.
And there's a small window at the top that says 0 with a little arrow next to it, and that's what you'll forward to the presentation.
Oh, got it. Okay, thanks. So I'm going to talk about the effects of cross-polar flights on Arctic temperature and also rerouting the flights on the Arctic Circle as opposed to going over the circle. Also a little about the overall impacts of black carbon on climate. So if we look at global warming today is between 0.8 and 0.9 degrees Celsius. This is the block on this graph shown here. It consists of a combination of greenhouse gas warming plus warming, black and brown carbon, primarily from fossil fuels and biofuels, a little bit of urban heat island offset by impact of cooling particles such as sulfates, nitrates, non-absorbing organic carbon, ammonia, and some other, and a lot of water associated with those compounds. And the total warming is half of it's offset by the cooling particles. So obviously, as you clean up air pollution particles, which include the soot particles and the particles, which is important to do because these cause 3 to 7 million deaths per year prematurely worldwide, you end up unmasking a lot of warming and warming even further. So, of course, the strategy, you want to clean up all the particles. One is to just control the carbon and brown carbon particles, which would help climate and health simultaneously, but you really need to control everything. So what we want to do is get rid of the warming gases, the black and brown carbon particles and the cooling particles simultaneously, then to ratchet down the global warming. And it can only really be done by changing energy types, so which ultimately, in terms of aircraft, would require changing to aircraft that don't emit any of fossil fuel or even biofuels, since biofuel energy requires a lot of carbon going to it, and also there's a lot of black carbon emissions associated with biofuel combustion. That's another story. But if I look at this is the global picture. But then if I look at the from the definition of temperature change, the top left panel shows the 2010 to 2013 warming versus 1951 to 1980, and it's around a 0.6 degree warming, but the Arctic is heavily impacted. And then the bottom left shows the same figure, but versus 1800 to 1930, showing about a 0.9 degree warming, although the data are more sparse. See, the Arctic is also significantly impacted. And the interchange for the Arctic, if we use a combination of these data and model estimates shown on the right, from the model I'm going to talk about the aircraft emissions, this, which is about a 1 degree warming of the globe, it's about a 5 degree warming of the Arctic since, well, at least since 1850, which the model shows, and the data are only showing from 1900 to 1930. So if let's 3 to 5 degrees, well, of that warming of the Arctic, so we calculated that about 1 degree Celsius is due to black and brown carbon, and which is a significant amount. So a lot of that black and brown carbon, most of it is from fossil fuels and biofuels that are transported in. But a portion, as we find here, is due to polar flights from aviation, which is the source of black carbon to the Arctic, except for ice-breaking ships and flaring in the Arctic region for natural gas drilling. And so, in fact, we'll find about 0.3 degrees of the warming could be across polar flights. And so let's see how we determine that. Well, cross-polar flights really only started in around 1998 after the Cold War ended, but they on and shows from 2004 to 2010 the number of flights per year. So they're on the order in 2010 about 56,000 flights. And what that I want to talk about, we looked at getting rid, or at least rerouting, those cross flights that were than 500 miles distance for aircraft that are 50 seats or larger, and had both origin and destination airports below the Arctic Circle, which is around 66 north. And so it represents about 80% of the cross-polar flights. And we actually were treating each of the 30 million flights per year worldwide from aircraft, and we were treating commercial flights. And these inventory for each flight from the Volpe National Transportation Center, and we're in 2006 data for that. And so we were every single flight individually, and looking at then rerouting every single flight across the poles individually. I'll show you some information about them. First, though, if we look at the vertical distribution of aircraft emissions from all 30 million commercial flights worldwide, there's some interesting statistics. The Tropopause height, based on psi frequency, the colors indicate where the aircraft emissions are relative to Tropopause. And interesting statistics are that about 74% of all aircraft emissions worldwide, commercial aircraft emissions, 74% of the emissions above the circle are in the stratosphere, which is extremely stable, of course. And 47% of the emissions from 40 to 90 degrees north are in the stratosphere. About 24% of global emissions are in the stratosphere, with 30% in January and 13% in July. 34% of all global emissions from aircraft are in regions of high static stability. But you'll notice that virtually all aircraft emissions over Arctic are going to be in the stratosphere. And this is, and you have something like black carbon, it turns out that it takes about 7 days, so emissions at 11 kilometers in the stratosphere, in the Arctic. It takes 70 days for 50% of the emissions to just descend to the surface. And then that's, it will vary by season, but it takes a long time. The particles, they last a long time, and so remove very quickly. So black carbon, only 11 kilometers over the Arctic, it's going to sit there for a long time, and it's going to have an impact for this period. Now, if we, this shows the original baseline emission inventory that we're using for all flights worldwide, and a rerouting inventory where we rerouted individual for going over the Arctic Circle, around the Arctic Circle, and we'll show you how we did that in a second. You can see that the pathway change, it reduces, and these are, by the way, these are CO2 emissions from those aircraft flights. So you reduce quite a bit of the CO2 going over the Arctic, about 83%, in fact, of the CO2 going over the Arctic and also the black carbon. But rerouting requires slightly higher fuel use, it turns out, because you go over slightly longer distances. And the numbers on that in the end. What it does is, in terms of the particles, it moves the particles to lower latitudes where they're more readily rained out. And so the mate rates of the particles much faster than they are over the Arctic Circle. And this has a big impact on addressing the climate impacts over the Arctic, because over the Arctic Circle, as I mentioned, the emissions, they last so long, they stay so long, whereas if you move them to southern latitudes, then they get removed much faster. And so this can have a benefit, particularly in terms of black carbon removal. In terms of the emissions over the Arctic, well, first, air emissions Arctic Circle represent about 0.75% of all fossil fuel emissions. So, yes, 0.75% of all fossil fuel emissions. The per unit meter, per square meter, over the Arctic Circle are about 20% those of the average CO2 emissions, because those emissions are concentrated in a pretty small area, because it's the pole, you converge as you go towards the poles. So there is quite a high density of emissions over the Arctic Circle, even though the mass of emissions is not large. Now, here's an example of how we'd reroute flights around the circle. This is a flight from Frankfurt to Anchorage, Alaska. And initially it's going over the Arctic Circle, but we rerouted it around the Arctic Circle based on pathways of similar flights. So this rerouting work was done by MITRE Corporation, whereas the inventory original one was developed by Volpe. But they actually did recalculation of the least cost method of rerouting each individual flight. So this shows an example pathway of that. The model that we developed to treat individual aircraft flights, it not only treats each plume, each aircraft plume individually, but it treats the extension of the plume and the spring, the shearing of the plume, and chemistry inside of each plume, and conformation within each plume. So this is an example of the subgrid plume model inside of the global model, which is Gator GMOM. And the subgrid plume model, it's the analytical equations treating ellipse, and a function, the shearing and spreading of the ellipse is a function of the grid diffusion coefficients and wind shear. And if you compare the model prediction, for example, of plume spreading and shearing on the left with large eddy simulation for the actual aircraft simulation under the same conditions, you can see that it's giving similar results, but the subgrid plume expansion model is you calculate lightning fast because it's actually an analytical solution. That idea of the and sharing, but we also do the chemistry, and as I mentioned, we do result conformation and aerosol evolution within each of the plumes. Now, this is a diagram of the contrail cloud fraction looking at the Earth from the model from a baseline case without rerouting. And on the right side, it shows the cross-section of contrails and zero lines indicating that the contrails exist all the way to the pole, to the Arctic, are concentrated primarily at latitudes. And slightly different contrail metrics when we do rerouting, but I don't have the figure to show that right here. Here's maybe the crux of the temperature change. So when we did a simulation with normal aircraft impulsions, and then routed all the flights around the Arctic Circle instead of going over the Arctic Circle, what we see is a drop of temperature on average over the Arctic Circle by a peak of around 0.3 degrees Kelvin or Celsius. And this was statistically significant. Now, the temperature changes in most of the rest of the lower latitudes are not statistically significant. The Arctic temperature change was. This was after over a 20-year simulation, so it took us out a lot of the results. So there was a reduction, and this was due to the fact that we did reduce the black carbon significantly, even a slight increase in fuel use. And so over a longer period of time, since you have higher CO2 emissions, this temperature change can be eroded. But at least over this period, where you save the Arctic sea ice, then there was a significant impact. And it was consistent with our global simulations accounting for all sources of black carbon over the Arctic, where we found about a 1 degree Kelvin increase. And also from our simulations accounting for all anthropogenic sources over the world and Arctic, where we found up to 5 degrees Celsius increased temperatures over the Arctic from greenhouse gases plus particles. And so there are a lot of effects that this was due to, including the effects of black carbon, but also not only direct heating from black carbon, but also impacts feeding back to clouds when we get into the troposphere. Some small impacts on the sea ice, but not significant on the sea ice. I mean, there were impacts of the warming on the sea ice, or the cool case. But the black carbon deposition to the sea ice, there's not a lot of it compared with the other sources of black carbon that would affect the sea ice directly. So if I summarize the impact, just here some numbers. There was an increase of fuel use by routing of about 0.056%, increase of the distance traveled by about 0.026% compared with all aircraft flights worldwide, that is. Reduced fuel use in the Arctic Circle by about 83%. Baseline cost of jet fuel worldwide is about $122 billion a year. The added cost due to rerouting was about $9 million per year, with $68 million due to additional fuel costs and $31 million due to operational costs. Estimated global warming cost to the U.S. in 2025 is about $70 billion per year, which accounts for severe weather changes, real estate impacts, energy impacts, and water impacts. The reduction in global warming by rerouting to about 1.7 to 2% of net global warming to date, and so that reduced cost to the U.S. would be about $4.7 to $5 billion per year. Is about 47 to 55 times the cost of rerouting, which was $100 million per year. So this seemed like if these numbers were correct, then there is an advantage in terms of cost and reducing climate impacts, at least in the near time frame, of rerouting these flights. Of course, eliminating the flights altogether or converting to different types of aircraft or different types of fuel, hydrogen fuel, for example, would eliminate carbon and black carbon emissions is another alternative. You can also do partial rerouting, which is reroute time flights, but you'll still allow nighttime flights, for example. There are many possible ways to address this, but the aircraft do seem to have a significant impact, which makes sense since they are one of the sources of emissions to the Arctic. So I'll up there and answer any questions.
We're all sitting and looking at your last slide. I'm sorry, Mark. We're looking at your last slide now and marveling at the numbers. And when you said if these numbers are correct, Ralph was emphatically shaking his head, saying those numbers are correct. So I think that's probably opening up the floor now to some I'm sure people will have some questions about this. Does anybody want to unmute and ask a question directly?
Yeah, Martin here again, Martin Jeffries. Thank you, very interesting. And my question was, you've conducted a numerical experiment here, a computer simulation, yet a natural experiment, if you will, of this kind was done the 1980s and early 1990s when the Soviet Union dissolved. Before that, there were many, many truly transpolar flights between Anchorage, Alaska, and many European destinations each day, and in the opposite direction, many European destinations to Anchorage, because they couldn't fly through what was then Soviet airspace. The Soviet Union dissolved, then what now the Russian airspace was opened up to these flights. So there was a big reduction of flights which were between Anchorage and Europe were going out over the Arctic pack ice, across the Canadian Arctic, across Greenland, before the Atlantic and into Europe. Has investigated the consequences of that natural experiment, if you will, on the reduction in black carbon loading and its the heat consequences of that.
I'm aware of anybody looking at that. I think it would have to be done with a numerical experiment because the data are just the amount of emissions from aircraft are pretty small compared to the emissions from all other sources, and we didn't have the satellite information in the vertical back then. It would be a numerical experiment as well. So it's hard to do this study by just looking at the data alone. I mean, combination of the data plus modeling, I think.
In that experiment, you do know the number. You would know the number of flights that were reduced, and the reduction in use and black carbon generation and so on. So you have better inputs to your model, be better calibrated and initiated.
One other difference is this study in particular, we actually had the pathway of every single flight, whereas and we can guess what some of the paths are, but to actually have information of that, what height they were and how much emitting at each height and their speeds and their the weather, that to affect their speed and everything. We didn't have that information. There's a lot more detail and information I actually have about the flights, because then we're actually able to treat each flight individually here. And back then we have bulk information, but we don't have flight by flight information.
Couldn't you use fuel use? Couldn't fuels give you some handle on how much was burned?
They only give us. You might have fuel use for the United States aircraft, so you know how much the total fuel use U.S. aircraft. Well, I can't speak for Volpe. They might have secret data that has all sorts of information, but the bulk data are just not enough for this year to run it. I mean, because Volpe only produced 2 or 3 flight-by-flight inventories ever. One was in 2004, one was in 2006, and they might have one. That might still be the only 2. In fact, but they went at an aggregate level even, and so you could probably do one. It just requires a huge effort, and it's reconstructing all stuff. Because right now they do it based on different. Technically based on radar information, and so actually have information about all the individual flights, but I don't know how easy it is to dig back that far to find all the flight information.
This is Jill. I'm going to a question here from Kelly Faulkner, which is for Mark, but I'm also going to remind everybody we're moving into the part of our webinar now where the floor is going to be open for discussion and questions for all 3 of our speakers. And but I will now ask the question from Kelly Faulkner, and she asks, examine the crowding impacts at lower latitudes for rerouted flights.
So the rerouted inventory accounts for the flights of the other aircraft. So they're at altitudes that are different. They're not in the same pathways. So it was done very meticulously, but it's become more crowded. So there is more logistically. But I should note that if you look at the 2050 emission inventory for that EA has put out, Volpe produced a 2050 mission inventory, not a flight-by-flight inventory, but an aggregate inventory that's gridded. They estimate that aircraft emissions in 2050 are going to be 5 times higher than today. This is, and I don't know if that's actually, because I think there was costs are going to go up, etc., and that that would really result in crowding. So that crowding was much greater than you'd see with this rerouting inventory.
Questions for our audience? Please feel free to unmute and ask.
Lieutenant Martin, if we're in the general question period now, could I ask my question of Trish?
Please.
Hi, Lieutenant Martin. Thanks for your talk. We know that the black carbon burden in the Arctic has decreased over the years, and largely due to reductions in production in Russia, is my understanding. Yet at the same time, I think an increase in forest fires in the boreal forest, and the projections are that this will increase. Has anyone investigated or done any work on whether this increase in black carbon from forest fires will reverse the downward trend due to the increase in black carbon from Russian sources?
Yeah, it's very easy to see the decrease in black carbon at the surface in the Arctic because we have these routine measurements, as you're well aware. But we don't have that much information about trends for smoke that are coming in at higher altitude, but maybe RAF now has a better look at that than, because we certainly can't see them sitting at the surface. So you can't compile all of the aircraft flights that have been done over the past several decades in the Arctic, and you also see a decreasing trend at higher altitudes in black carbon, but again, those are just snapshots, and you're not really looking particularly at forest fire plumes or, the summertime. They've usually been done in the spring to look at decays. I think we would have to look at something like the measurements to see if you could detect any long-term trend in higher up smoke plumes. Maybe Ralph could comment.
Sage would be pretty useful too, probably. And if you could do inventory at public, characterization of the forces. You'd then need a model, of course, to determine how much that gets up to the region. But forces that we have, then there are the Aeronet stations, which would then give us some validation. It'd be a pretty much task, but it could be done.
We have another question from Marcus. I don't have a last name, and it's a very long question. I'm going to invite Marcus, if he's online with a phone, to unmute and ask the question directly. If he's able to do that, then I will read it for our audience and speakers.
Sure, I can do that. So my question relates to a phenomenon that was discussed in the Schindel paper in 2009 that showed some Arctic cooling from be in the Arctic. They didn't include snow albedo effect and some other things, so this is something that was, sort of oddity, but I think both Maria Sand and Mark Flanner in separate papers sort of looked into this and found that high altitude BC in the Arctic could, because of shading and heat transport effects, also cause this surface cooling. And so I'm wondering if you see any of this in your work, or, obviously the aircraft are indicating into high altitudes. I imagine that your model is getting a different result from their models. And if you could discuss that. Thank you.
Sure. I have to pick over that paper. They don't include well, either Geocell or Mark Flanner or the other model, they do not include what are called cloud absorption effects, which is absorption black carbon within cloud drop or within ice crystals or between cloud drops or ice crystals. And so this is a very strong and important impact, especially cloud, cirrus cloud, because the heating of a cirrus cloud, it can actually, if you include black carbon inside an ice crystal, that ice crystal is about 50 times higher than if you don't include that absorption, and so you can melt the crystals faster. So that was one of the things that none of that is included, and so I suspect that's part of it. Also, they weren't looking at the other kind of the emissions from the aircraft. They're looking isolated at black carbon as opposed to aircraft emissions are contained with black carbon and organic carbon coating and some sulfate coating, which enhances the absorption. So you get the coating effect, the optical focusing effect of the carbon, and you also form the contrails from the emissions of aircraft, and so that's another thing. So there's a difference in the type of simulation that's run if you're just looking at carbon alone versus the black carbon in the context of aircraft emissions. But I think more important was this cloud absorption effect that included in those studies.
Do we have any other questions from the audience? Well, we're getting close to the end of the time that we had allotted for this webinar. I think that these three talks were terribly interesting, all very different. I think I'll close maybe with a comment that Trish said a lot of the estimates about what black carbon occurring in the Arctic is based on these inventories and emissions and trajectory models. Ralph talked about some of the difficulties that we have with actually directly observing proxies for black carbon in the Arctic with satellites. I attest to the fact that doing observations at the surface from observatories is also very difficult since we're limited in any other ways that could be the subject of a whole other talk about how we can observe black carbon that way. Mark has talked about this very interesting phenomenon and possible impact that we can have with these aircraft, which, as far as I know from our previous seminars with the EPA and DOE and DOI and State Department people, I don't think they seem to be taking it into the aircraft inventories into account very much. And then on top of all of that, we have an issue of once we get a fix, or if we can get a fix on what kind of black carbon there is in the Arctic, we have to really move on to what the impacts are on the environment and understand the processes by which black carbon are actually affecting the Arctic environment, and then as that goes down to the rest of the planet. So it seems to me like we have a very, very difficult but very, very important problem here that's going to require a lot of synthesis. Again, I want to thank all our speakers, and the original intent for this was to inform this IARPIC atmospheric implementation team to see how these agencies can be coordinating on addressing this problem, and I think you've given us a amount of information that's going to be informing our discussions probably for our next two meetings. I see a message here from Kelly Faulkner again saying thanks to the speakers and to me for hosting. Actually, I want to thank Sandy Starkweather here, who is running a lot of the controls and making this much easier. If anybody, and with that, I think I'm going to close this webinar off and thank everybody very much. We'll be looking forward to any other input that you might have, and we will be posting on the website summaries of these webinars. And I remind everybody that these presentations are online, and I believe that today's webinar has been recorded. So I'll hear lots of beep, 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 beep as everybody hangs up now.
Hey, I'm still on.
Thanks, Neil.
Have a weekend, everybody.
Thanks. Neil, before you go, you need to transfer the host privileges back to Andy, and he can close out the webinar.
That was presenter, so if you right-click on my name, you should have an option for transfer host.
Thanks, Andy, actually.
And Andy, if you could send me the file, then I'll get it uploaded to the website on Monday.
Yeah, I'll start the recording or like the conversion tonight. It'll take about an hour and a half.
Okay.
I'll send it to you on, or I'll to find a way that I can send it to you on Monday.
Okay.
Okay?
All right. Thanks a lot, everybody.
Okay. Thank you.